So, hello everyone, a very good afternoon everyone. I welcome you all to the YouTube platform of IMS GATE Academy. So, this fundamental series is for strength of material to make your basics of strength of material so strong that when it comes to the application part of the concept, it becomes very easy for you. If you know the basics of any subject, obviously its application part becomes easy. And the questions that we have seen over the period of time for last 4-5 years in GATE examination, they are more application based. That's why we are conducting this IMS, that's why we are conducting this foundation course for strength of material. Just please like and share the session with all your friends so that even they can have a benefit of understanding all the small concepts that are there for strength of material, so that they can understand the complicated concepts in a better fashion and they can apply it even better, right? So, in the previous session, we have discussed about how the loads are applied over any body, and we have seen that in our entire discussion of strength of material, the loads will be gradually applied load, and we will be talking about elastic bodies, right? Elastic bodies are those bodies when load is applied over them, they will undergo some amount of deformation, or they will show some amount of deformation, okay? Now, today we will talk about, once we apply load over any body, how the body will behave towards that load. In order to explain that behavior, we need to understand one term. I think you might have heard about this term, stress. But I want to ask you, what do you really understand by the term stress? Do you exactly feel what we mean by stress? Okay. So, most of us know stress as it is just load divided by area. Whatever is the external load divided by area. No. External load divided by area is termed as pressure, and that is a totally different theory. Okay. We will be discussing about stress, and if I say the word stress, I am stressing on the word stress, right? So, that stress is nothing but the internal resistance offered by the body per unit area. Okay. So, let us see this. If you observe this body, for suppose this is my body, over this body I have applied some amount of load. Okay, this is my body. For this body, I have applied this load like this. This is the load that I have applied over this body, right? And which type of loading is this? This is a gradually applied load that we have already seen, okay? When you apply load over this body will try to undergo deformation. This body will try to undergo deformation like this. This body will try to undergo deformation, right? So, this is the deformed shape of the body. This is my deformed shape of the body, right? In order to restrain this elongation or deformation, this body will provide the restraining force. So, the restraining force that this body will going to provide, if you look into this cross section, in order to restrict whatever this load is doing to this body, there will be some internal resisting force that will develop in the body like this, right? So, this is my internal resisting force that is developed in the body, and this internal resisting force will going to resist the effect caused by this external load P. So, P is my external load, P is my external load, P is my external load or external force, and R is the internal resisting force, internal resisting force. internal resisting force. And why this internal resisting force is developed? This internal resisting force is developed to restrict the deformation of the body, which is caused by this external load. Okay. This internal resisting force per unit area is termed as stress. Okay. So what is stress? So your stress is internal resisting force per unit area. Stress is internal resisting force per unit area, right? Now, if you just consider the equilibrium of this system, if this is my system, and if you consider the equilibrium of this system, right? If I draw this system, so this is my system like this. This is the section, right? This is my section. This is the external load P. In order to restrict this deformation caused by this external load P, internal resisting force will develop inside this body. So this is my internal resisting force. Also at the same time, the body should be in static equilibrium, which means that summation of horizontal forces should be equal to 0, which is gives us as P should be equal to R, right? So what I mean to say is, your internal resisting force is equal to the external load applied. So your internal resisting force is equal to the external force applied. That's why we write stress is equals to, load divided by area. Because this external load P is equal to the internal resisting force R. That's why we write this. But what happens usually is, when the students see this formula, they try to figure out that the stress is nothing but whatever is the load applied per unit area. No. If I talk about the external load, so external load per unit area is termed as pressure. But the internal resisting force per unit area is termed as stress. So this stress is nothing but your internal resisting force per unit area. I hope you got this very clarity on this topic, right? So next time, if any statement you see in any of the technical examination, not just GATE, that what is stress or define stress, never mark it as load per unit area. It will always be internal resisting force per unit area, and that is what we mean by stress, right? On the other hand, if I have to write pressure, so pressure is external load per unit area. So this is the basic difference between stress and pressure. Stress is internal resisting force per unit area and pressure is external load per unit area. Now the thing is, if you look into this diagram very carefully, you will notice that initially the area of the section was A0. Initially the area of the section was A0. Initially, this is my initial area. Initially, the area of the section was A0. And when you have applied the external load, this body undergoes deformation and some change in cross-sectional area is seen. So the instantaneous area which is there is termed as A actual. So this AA is nothing but the actual area when body has undergone deformation, or the instantaneous area when body is undergoing deformation. Means at any time when the body undergoes deformation, what is the actual area is AA. The original area is A naught. So the next question comes is, sir, which area to use? You have told us that stress is nothing but internal resisting force per unit area. But which area to use? Actual area or initial area? That is again one of the question that usually happens to the student, right? Okay, so depending on the type of area we are using to calculate the stress, we have defined stress like that, right? So the next topic of discussion is different types of stress. Different types of stress. So basically, depending on the type of area you are using, stresses are defined as two types. First one is known as the engineering stress. First one is known as the engineering stress or nominal stress. First type of stress is known as engineering stress or nominal stress. For engineering stress and nominal stress, it is calculated as sigma naught is equals to resisting force per unit original area. So whenever you will be using original area for calculating the stress, that stress is termed as engineering stress or nominal stress. So A naught is your original area. A naught is your original area, right? But if you are using the instantaneous area or the actual area, that is the reduced area when you have applied the tensile stress, or the enlarged area when you have applied the compressive stress or the compressive force, not stress, sorry. When you have applied the compressive force, that that stress is known as the actual stress. Actual or true stress. Actual or true stress. So actual or true stress, sigma actual, sigma A, is equals to the resisting force per unit actual area. AA is nothing but actual or the instantaneous area. So this AA is actual area. So this is how we have usually defined the stresses. In our entire calculation in strength of material, we will be using engineering stress only, because we need to keep this area to be constant in our entire analysis. If you just compare this A naught with A actual, you will find that there is not much difference. Though there will be some difference, but there is not much difference. So every time we will going to analyze any body, we will be using this engineering stress or normal stress. Okay. So depending on the type of area we are using, stresses are classified as two types: engineering stress, and second one is your actual stress. Okay. Now, if you observe closely, you will find that, let me consider first case, that is, if you have a body like this, for suppose you have a body like this, and over this body you have applied the tensile load. This is the tensile load that you have applied. This is the tensile load that you have applied, right? So it is very easy to imagine that when you apply the tensile load over this body, this cross-sectional area will going to reduce, right? So if A naught is your actual area, original area, on applying the tensile load, this cross-sectional area will going to reduce. This cross-sectional area will going to reduce, right? Now the new cross-sectional area looks like this. This is my new cross-sectional area. This is my new cross-sectional area, okay? And it is very much clear that this new cross-sectional area, that is the actual area, is less than your original area. So for the case of tension, your A naught is more than actual area because the area is getting thinned, okay? So if A naught is less than A actual, it is very much clear that when you write the engineering stress, which is sigma naught is equals to the resisting force per unit original area, and when you write the actual stress, which is nothing but your resisting force per unit actual area, and A naught is more than A, so clearly we can say that your your engineering stress will be less than your actual stress. Your engineering stress will be less than your actual stress. So in case of tension, your engineering stress is less than the actual stress. Engineering stress is less than actual stress. Similarly, if you consider the same body and you apply the compressive force, you can very clearly identify that if you apply compression, if you apply compressive force over this body, so this is my body. When you have applied the compressive force, so this is my compressive force P that I have applied over this body. When you apply the compressive force, this A naught is my original area, and on compressing, this cross-sectional area will going to expand, right? On compressing this body, this cross-sectional area will going to expand, and the new cross-sectional area will look like this. This is my new cross-sectional area. This is my new cross-sectional area, right? And it looks like A actual. And it is very much clear that my A actual is, or A naught is less than A actual. So whenever I have applied the compressive force, the cross-sectional area will going to increase, and that increased cross-sectional area is A actual, okay? If my A naught is less than A actual, then clearly I can say this, my engineering stress, which is written as resisting force per unit original area, and my actual stress, which is again resisting force divided by actual area, and if A actual is more than A naught, then my sigma actual will be less than sigma naught. So my sigma actual will be less than sigma naught. So sigma naught is more than sigma actual. So this is the relation between the actual stress and the engineering stress when you apply the different types of tensile load and the compressive load, okay? So I think this is very simple to you. So all these basics are pretty much required in order to analyze any structure. This should be clear in your mind whether that load will going to increase the area or it will going to decrease the area. So if any question appears as a statement that if you apply the tensile load, then which stress will be more? So obviously your engineering stress will be more. Sorry, your actual stress will be more. And when you apply the compressive force, which stress will be more? So your engineering stress will be more, right? So like that you can identify, Okay. So these are some of the basics about engineering stress and the actual stress. Moving to our next topic, which is strains. Okay. First of all, understand what do we mean by strain. I have already told you this, when a body or when over a body you apply the load. So if this is my body, on applying the load like this. So this is the external load that I have applied. L naught is the length of the body. This L naught is the length of the body. Okay. On applying this load, this body will going to deform and you will see the increase in length of this body. You will see the increase in length of this body like this. So this is the increase in length of the body, right? Now the new length is L dash. L dash is the new length of the body. L dash is the new length of the body. Originally, L naught was the length of the body. Now, L dash is the new length of the body after the body undergone some deformation. So, this change in length that happened is, so change in length is equal to, so change in length delta L is equal to L dash minus L naught, right? The strain is defined as change in length per unit length. So this strain is defined as change in length per unit length. Change in length per unit length, right? This change in length is nothing but delta L by length. Now again the question comes, here which length I should use to calculate the strain? Okay, strain is defined as change in length per unit length. Depending on the type of length we are using, same engineering strain is defined into two varieties. Okay, so strain is simple to you. So strain is nothing but change in length per unit length. Depending on the type of length we are using, this strain is defined into two categories. Okay, so let me define this strain into two categories. So here, when I talk about type of strains, so depending on the type of length you are using, which type of length you are using, this strain is also defined as engineering strain or nominal strain. Engineering strain or nominal strain, right? So engineering strain and nominal strain is defined as epsilon naught is equals to the change in length delta L divided by the original length L naught. So your engineering strain is defined as change in length per unit original length. So L naught is your original length. L naught is your original length. L naught is your original length. So change in length per unit original length is termed as your engineering strain, right? Similarly, the other variety of strain is known as the actual strain. The other variety of strain is known as the actual strain or the true strain Actual strain or true strain. So when we use the actual length, that is after deformation, if we are using the actual length, that is the instantaneous length, that is L dash, right? if you are using the instantaneous length or the actual length after the body get deformed, that type of strain is known as the actual strain or 2 strain. So this actual strain is defined as epsilon A, which is nothing but change in length divided by the instantaneous length L dash or the actual length L dash. So this actual strain is change in length per unit actual length. So this is how you have defined the different types of stresses and the different types of strains. The question is, the type of area you are using to calculate the stress. Depending on that, you have two types of stresses, engineering stress and the actual stress. Similarly, depending on the type of length you are using to calculate the strain, these strains are broadly classified into two types, actual strain and the engineering strain. Okay. So this is the classification. Now talking more about this actual strain and your engineering strain. So relation between true stress and the engineering stress. Okay, before that, if you observe this closely, this actual strain, which is nothing but delta L by L dash. This is your actual stress, right? This is your actual stress. Okay. So this is so this is delta L by L dash. This is your actual stress that we want, right? That we exactly want. Okay. Now moving on with this, you have one relation between true stress and the engineering stress. Okay. Observe this very carefully. If you have a plastic body, sorry, if you have a elastic body, if you have a elastic body, on applying load over this elastic body, the elastic body will undergo some deformation and you see the change in length of this body. And you see the change in length of this body. So this is your elastic deformation. For elastic deformation, we see the change in volume. Since the length and area is changing, so we see the change in volume of the body. We see change in volume of the body. Whereas if same body is analyzed under plastic state, so under plastic state, your volume remains constant and corresponding to that constant volume, you will going to see the change in dimensions of the body. So under plastic state or in plastic state, in plastic state, in plastic state, your volume is constant. Your volume is constant. Under plastic state, your volume is constant. So we can write that your initial volume, that is A naught into L naught, should be equal to A actual into L dash, right? So this is your A naught into L naught is your original volume and A actual into L dash is your instantaneous volume. That is after deformation, whatever will be the volume of the body, that is A dash into L. Okay. So when we look into the relation between this actual stress and the true stress, you have this relation sigma actual is equals to sigma naught into 1 plus minus epsilon naught. So there is one derivation regarding this. So you need to just keep a check under plastic state. When volume is constant, your A naught L naught should equal to A actual into L dash. So this is the relation that we have for actual stress and your engineering stress, right? So sigma actual is equals to sigma naught into 1 plus minus epsilon naught. So this is the direct relation that we have. You can derive this, right? But right now this derivation is not that important. So for now you can just have this relation directly, and this relation holds good even for elastic state, right? Though we have derived this relation through the plastic state, but this relation also holds good for elastic state. Okay, so I hope you have got this. Okay, so you can just note this down quickly so that we can move. Chalo, moving on with this. So depending on the type of areas we are using, the type of length we are using, we have defined the different types of stresses and strain. Now there is one more actual classification of stresses, right? And this is totally dependent on the nature of stress. So depending on the nature of stress, depending on or in terms of nature of stress, with respect to nature of stress, with respect to the nature of stress, stresses are classified into two types. Stresses are classified into two types. So first one is your normal stress, and second one is your shear stress. Second one is your shear stress. Okay. Now observe this. If this is my cross section, and over this cross section, if the stresses are acting perpendicular to the cross section, if the stresses are acting perpendicular to this cross section, so this is my cross section, this is my cross section, this is my cross section XX. If the stresses are acting perpendicular to the cross section, then this type of stress is termed as the normal stress. Okay. Similarly, if you again consider the cross section like this, so this is my cross section, this is my cross section, right? This is my cross section. For this cross section, if the stresses are acting along the surface, then this type of stress is termed as your shear stress, right? So if the stresses are acting perpendicular to the surface, then these stresses are known as normal stress, and if the stresses are acting along the surface, then these type of stresses are known as shear stress. So for normal stress, stresses act perpendicular to the surface. And for shear stress, stresses act along the surface. Right? You can visualize these two types of stresses by observing this. For suppose this is the load acting over the body. This is the direct load which is acting over the body. So in order to restrict this effect of this load P, your stresses will develop perpendicular to the surface like this. So this is your normal stresses. Similarly, if you consider one column, cylindrical column like this, for this cylindrical column, your load is acting perpendicular to the surface. Your load is acting perpendicular to the surface. So if you consider any section, for this section, the internal resisting force will be developed like this. So this will produce the stress perpendicular to the cross section. So whenever the stresses are produced perpendicular to the cross section, these type of stresses are known as normal stresses. These type of stresses are known as normal stresses. These type of stresses are known as normal stresses. Similarly, one more variety of normal stress is there. If you observe this beam, right, this is my cross section of the beam. And over this beam, a bending moment is applied like this. So this is my bending moment M that is applied over this beam. Okay. So due to this bending moment, these lower fibers will be under compression. These lower fibers will be under compression. These lower fibers will be under compression, and these upper fibers will be under tension. These upper fibers will be under tension. These upper fibers will be under tension, right? So if you just cut any cross section, and draw the stress distribution for this cross section. So if I draw the quick stress distribution for this cross section, so this is my cross section. This is my cross sectional area. For this cross sectional area, if I draw the stress distribution, right? If I draw the stress distribution. So the upper fibers are under tension. Upper fibers, that is the fiber that are present above, are under tension. These fibers are under tension, right? And this tension is decreasing like this. The lower fibers are under compression. The lower fibers are under compression. These lower fibers are under compression like this. These lower fibers are under compression. And this compression increases from neutral axis, from the center point to the extreme fibers. As you move above from the central point, you will find that your stresses or the normal stresses are increasing. Similarly, when you move down from the neutral point or the neutral axis, you will find that your normal compressive stresses are increasing, right? So this is the stress distribution for a beam under bending. So when you just observe the beam under bending, you will find that if the beam is bending like this, this moment has a tendency to bend the beam like this. If the beam is bending like this, the upper fibers will be under tension and the lower fibers will be under compression. So if we just plot the stress distribution, you will find that the upper fibers stress is increasing from neutral axis till the uppermost fiber, and similarly if you talk about the lower fibers, they are under compression. So this entire thing is under tension. This is tensile stresses, and these are compressive stresses. And when you look into the stresses and how they are acting, you will find that if this is my cross section, these stresses are acting perpendicular to the cross section. And if the stresses are acting perpendicular to the cross section, it is very easy to define them. So the stresses which are acting perpendicular to the cross section are termed as the normal stresses. Okay. So based on these two diagrams, I'll just define this. So normal stresses are again of two types. Normal stresses are again of two types. And first of all, what are normal stresses? Normal stresses are those stresses which act perpendicular to the cross section. Act perpendicular to the cross section. So normal stresses are of two types: direct stress, direct stress, where when you have applied the load directly over the cross sectional area, where you have applied the load directly over the cross sectional area like this load will going to cause compressive stresses in the entire cross section, and the same amount of compressive stresses are developed in the entire cross section. So these type of stresses are known as direct stresses. The second type of normal stresses is known as bending stresses. And we have just now seen, if you consider any beam like this, if you consider any beam and you apply a bending moment like this, right? If you apply the bending moment like this, you have the stress distribution like this. So this is my stress distribution. The upper fibers are under tension, the lower fibers are under compression. So this is under tension and this is under compression. But all these stresses are acting perpendicular to the surface, hence they are defined as the normal stresses, right? So direct stresses are also of two types: tensile and compressive. Tensile direct stress or compressive direct stress. Similarly, your bending stresses will be also of two types: tensile bending stress and the compressive bending stress. Okay. Moving on with this, the next type of stress is known as the shear stress. As the diagram is in front of you, you have these two blocks, right? When you apply the force, shearing force, that is force which is along the surface. This force F, that is the shear force, is along the surface. And this violet area you can see very clearly. This violet area is the resisting area which resists this shear force F, which is acting along the surface. So if the force is acting along the surface, that force is termed as the shear force. First of all, if the force is acting along the surface, if the force is acting along the surface, force is acting along the surface, is termed as shear force. So if this force is acting along the surface, right, what you have to do is, you have to just place your hand over this block and you have to just slide this block in this direction, right? So if you are sliding this block in this direction, it is very easy to imagine how the shear force will be acting over this block. In order to restrict the deformation caused by this force, this cross-sectional area will be used. Okay, so I'll just draw this. If this is my block earlier, if this is my block, and this is the kind of force I am applying, right? So this force will try to deform this block, but this area which is present, this area which is present, right, this area will try to restrict the effect caused by this force. So the shear stress is defined as the shear force per unit this resisting area. So this area that I have drawn is termed as resisting area. So shear stress denoted by tau is defined as your shear force divided by the resisting area. Shear force divided by the resisting area. Okay. Once again, if you have this block, right? This is the block that you have. Okay. Over this block, if you apply the shear force like this, right? This shear force will try to deform this section, and this deformation will happen like this. This deformation will be like this. So this is the kind of deformation that will be happening due to this force. Okay. So if this is my height h, if this is my height h, this is my height h, this is the change in length delta L, right? This is the change in length delta L that happened because of this block getting tilted by some amount. So this angle is termed as your shear strain. This angle of tilt that happened when you have applied the shear force over the block, this angle is termed as your shear strain. So shear strain is nothing but your delta L by H. So this H is your height of the block and delta L is this change in length, right? And obviously this delta L will be equal to this delta L. So this is also delta L. So this is also phi. And this phi is nothing but your shear strain. This phi is your shear strain, right? So your shear strain is phi, which is defined as delta L by H, okay? So whenever you apply the shear force any body, this body will going to deform in this fashion, and the angle of tilt that happened, this is termed as your shear strain, and this shear strain is equal to delta L by H, right? So I hope shear stress and shear strain is clear to you. Whenever you need to calculate the shear force, you will use that area which is restricting or resisting the effect of this force. So the effect of this force is resisted by this resisting area, right? This is the resisting area. This is my resisting area. This is my resisting area. This is my resisting area that will going to resist the effect of this shear force F. So the shear stress is defined as the shear force per unit area. Okay. Moving on with this. So here is one question. This is again a simple question in order to develop your basics. The question says that a bearing pad consisting of a flexible material. Okay. So you have one bearing pad. What is a bearing pad? Bearing pad is that pad which absorbs shock loading or which absorbs impact loading. Okay. So any pad which can absorb load is termed as a bearing pad. Okay. So simple thing is there, you can imagine a pad of rubber. Okay. So a pad of rubber, if you drop anything over a pad of rubber, that will going to absorb this impact or shock loading. Okay. So you have one surface like this, this is my surface. Over this surface, you have a bearing pad. This is my bearing pad. This is my bearing pad, and this is flexible. This is a flexible pad, means it can just move like this, right? It's a flexible pad. Just imagine this as a rubber pad, nothing more than that. So a bearing pad consisting of a flexible material of thickness 10 mm. So this thickness is 10 mm. Next is capped by a thin steel plate of dimension 50 cross 75 mm. So above this you have a steel plate. So this will be my steel plate. Okay, I'll take this. So this is my steel plate. So this is my steel plate, right? This is my steel plate. Dimension of this steel plate is 50 by 75 mm. These are the dimensions of my steel plate. It is subjected to the horizontal shear force of 5 kilonewton. So we have applied the horizontal shear force of 5 kilonewton over this steel plate. This is the horizontal shear force of 5 kilonewton over this steel plate. So when this steel plate is attached to this bearing pad, what will happen is, this steel plate will try to move in the forward direction, but this bearing pad will try to restrict the motion of this steel plate, right? So you have applied the shear force in the horizontal direction, and the magnitude of that shear force is 5 kilonewton. So the shear force, due to the shear force, this steel plate will try to move in the forward direction, but this flexible pad will try to restrict the motion. So when you look into the final picture, this steel plate will going to bend this flexible pad. This steel plate will going to bend this flexible pad. This steel plate will going to bend this flexible pad, right? This steel plate will going to bend the flexible pad like this. So this is the new position of your flexible pad. This is the new position of your flexible pad. This is the new position of your flexible pad. This flexible pad is deformed by some angle phi. So there is some amount of shear strain that happened over this flexible pad when this flexible pad is getting moved by some amount phi. So there is some amount of shear stress that came over this flexible pad. Okay. Now the question is asking to determine the average shear stress. So this question is very simple. So your average shear stress tau is equal to the shear force per unit resisting area. Shear force is equals to, shear stress is equals to shear force per unit resisting area. Shear force is given to us as 5 kilonewton. So I'll write this as 5 kilonewton, so 5 into 1000. Then your resisting area will be this area which is resisting the effect of shear force. And the area which is resisting the effect of shear force is nothing but 50 cross 75. So this is 50 cross 75. So this is the resisting area. So this numerator is in Newton and denominator is in mm. So you can just calculate mm square, So you can just calculate the shear stress in Newton per mm square. So do the calculation quickly. So this is like 5000 divided by 50 into 75. So this shear stress comes out to be 1.33 Newton per mm square. Okay. So this is the average shear stress that is there, which is developed over this flexible pad which is there, right? So I hope this question is very much clear to you, and this question is an easy question for you, right? Moving on with this, I would like to discuss two units. So if you look into the unit of stress, stress is resisting force per unit area. So if the resisting force is in Newton and area is in meter square, so this is one of the unit of representing the stress. This Newton per meter square is also known as pascals. This Newton per meter square is also known as pascals, right? So basically the unit for measuring the stress is pascals, and 1 pascal is equals to 1 Newton per meter square. So 1 pascal is equal to Newton per meter square. Okay. Just convert this meter square into mm. So in order to convert this meter square into mm, what I have to do is, so this is nothing but Newton divided by 10 raised power 6, this into mm. So this is 10 raised power 6 mm square, and this is equal to 1 pascal. So 1 n divided by 10 raised power 6 mm square is equals to 1 pascal. Just take this 10 raised power 6 to the other side, you will have, so 10 raised to the power 6 pascal is equals to Newton per mm square. So wherever 10 raised to power 6 is there, you have to write it as mega. You have to write this as mega. So 1 Newton per mm square, 1 Newton per mm square is equal to 1 megapascal, is equals to 1 megapascal. So 10 raised to power 6 into pascals is megapascal. So 1 Newton per mm square is equals to 1 megapascal. So these two relations you should also keep in mind. So unit for measuring stress is pascals, and 1 pascal is equals to Newton per meter square. When you convert this meter square into mm square, you have to write 10 raised to power 6. Okay. So Newton divided by 10 raised to power 6 mm square is equals to 1 pascal. So from here we get 1 Newton per mm square is equals to 1 megapascal. Similarly, if you look into the unit for strain, if you look into the unit for strain, so strain is nothing but change in length divided by the original length, or whatever length. Original length or actual length, it doesn't matter. That defines the type of strain. Okay. So strain is change in length per unit length. So if you write the units of these two, it will be either meter per meter or mm per mm. Right. So these two units will going to cancel each other, and you will find that your strain is unitless. It is unitless. So your strain is unitless. So if I talk about strain, strain is unitless. Unit of stress is pascals, Newton per meter square or Newton per mm square. And 1 Newton per mm square is equals to 1 megapascal. Okay. So I hope this is also clear to you. Moving on with this next. Okay. So now moving on to our next principle, and next principle is again an important principle which is known as Saint-Venant's principle. Although the effect of Saint-Venant principle will not be considered in the entire theory of strength of material, but you should be aware about this fact. This principle is for the stress concentration. This principle defines the stress concentration. So, this Saint-Venant principle defines the stress concentration. This Saint-Venant principle defines stress concentration. Stress concentration. Okay. Now the thing is, what is exactly stress concentration? So here I have considered one example. When you apply load over this body, say the load applied is P over this body, right? So how do we apply this external load? So you will just going to hold this body from this point and you will going to pull it. Okay. What you did, how you apply the point load? You will going to just grab that body from that point and will going to pull it. For suppose this is my body, and if I have to apply the point load, I will just hold this body and I will going to apply the tensile load or the compressive load, whatever I want. So whenever we are holding a body from a particular point and we are applying the point load, at that time what happens is, in this area, stress concentration takes place. In this area, stress concentration takes place. On what is stress concentration? Stress concentration means your stress will not be uniformly distributed across the cross section. If you just cut the cross section at a distance of b by 2, you will find that your stress varies like this. Your stress varies like this. This is your stress variation, right? So your stress varies like this. This is your stress variation, and this is at a distance of b by 2, and b is nothing but this width b of the member. If you go at a distance of b by 2 along the length, your stress varies like this, and the maximum stress, this is your maximum stress, this is your maximum stress, this is your maximum stress, and this is your average stress. This is your average stress. So your sigma max is equal to 1.387 times of average stress. Means the variation between the maximum stress and the average stress is more when you have just moved down by the amount of b by 2 length in this member. If you move by the amount of b length in this member, now again you will see the stress concentration, and this stress concentration will have somewhat same variation, like this, will somewhat have same variation like this. So this is the stress concentration that we have. This is the stress concentration that we have. But this time your maximum stress, this is your maximum stress, and this is your average stress. This is your average stress. The maximum stress is only 1.027 times of your average stress. Okay. And finally, when you move 3b by 2 length inside the member, your stress variation will be uniform throughout the cross section. Your stress variation will be uniform throughout the cross section. Okay. So whatever theory we discussed, that your stress is uniform throughout the cross section in case of point load or direct loading, that is only applicable when you have moved 3 by 2 length inside the member. till this length, if you consider this part, for this part, you will going to have a stress concentration. You will going to have a stress concentration. And what is stress concentration? When your stress is not uniform across the cross section, that is termed as your stress concentration. Okay. So only when you have moved in by the amount of 3b by 2 inside the member from both the ends, right? So if you consider this and if you consider this, right? So if this is my 3b by 2 and this is also my 3b by 2, this length is 3b by 2 and this length is also 3b by 2. So beyond this length, in this area, you will going to have uniform, in this area, right? In this area, you will going to have uniform stress. In this area, you will going to have uniform stress. This is the area in which you have uniform stress. So in this area, you have uniform stress. And in these two areas, you have stress concentration. In these two areas, you will going to have stress concentration. So that is what explained by Sir Saint-Venant, that in the areas up to length 3b by 2, where b is the width of the member, for these two areas you will going to have stress concentration, and for the remaining part the stresses will be uniformly distributed, and that is what is explained by Sir Saint-Venant. Okay, so I hope this is clear to you. All these basics are clear to you. I hope all these basics are clear to you, right? So these are the basics about stresses and strain. In the next session, we will going to start with the Hooke's law, and we will going to check the different numericals that are there for the Hooke's law, and we will see about what are the different elastic constants which are there and how Hooke's law is used to calculate shear stress and the volumetric strain for different types of body. So that is all for today. I hope you got a lot of information today regarding the basics of stresses and strain. Thank you so much for watching patiently, and do check our channel and follow us regularly to get all the updates regarding the fundamental series and also about the job notification that you will have as an update in our YouTube channel. So thank you so much for watching. Have a very good day.